Greetings and salutations. Welcome to part 2 of the level 2 NCEA chemistry structure and bonding paper. So this particular video we're going to continue and move on to question number 2. Now if you watch part 1 and you had some questions on the polarity part, like say how did I know I2 was polar, then this is the video to jump to, because the whole section, most of it is on polarity, and that's a guaranteed question. Okay, so let's, without further ado, let's just get into it. So this is question 2. If you look at this particular question, again, very standard Lewis diagrams, shapes of molecule, and polarity. You have to be able to do one to get the other than to get the other. Okay, so Lewis diagram is achieved section, and this is I have my method of doing this, and it works all the time in NCEA level 2, and it's really helpful if you're just last minute cramming this. So here it is. So look at this, CH4. So this is what I tend to do, CH4. Now if you are quite good at organic chemistry, you should know that carbon always bond 4 times. Not 100% of the time, but in NCEA level 2, yes it does. Hydrogen only bond once, oxygen bonds twice, nitrogen bonds 3 times, and then your chlorines, your bromines, your iodines bond only once. So these, you need to know these for organic anyway. So if you have CH4, you should just be able to draw them quite quickly, because you should, assuming you can do organic chemistry. But if you can't do organic chemistry, this is a method that works for all the molecules in year 12. And here we go. Okay, so for carbon, now the first thing you need to be able to do, just write them down like these. I have 1 carbon and 4 hydrogens. So I got 1 carbon and 4 hydrogens written here. I need to count how many valence electrons these guys actually have. So you need to look at the periodic table. Carbon is a group 14 element, so it has 4 valence electrons. Hydrogen has 1. Hydrogen, all of these hydrogen has 1 valence electrons. And then how many can they have maximum? Like say to have a full shell of this needs to have 8, this needs to have 2, this needs to have 2, this needs to have 2, and 2. So let's count. I need to have 8. The CH4 right now, the carbons and the hydrogen only have 8 valence electrons, but they need to have, if you add it up, there'll be 16. So that means they have to take the difference. You share 8 bonding electrons. So that means they need to share 8 electrons to be stable, and that will be 4 chemical bonds, because each line is 2 electrons. And we can come back and we can go, all right, hydrogen, see that line? So if you look at this, that's 2 electrons, happy, 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 and happy. And if you look at the carbon has got 1, 2, 3, 4 lines around it, and it has 8 electrons around it. Everyone's happy. So for NCl3, again, if we use this method, this works all the time in year 12. It doesn't work in year 13 anymore because of the expanded octet. But I personally think the year 13 one's actually easier to do. So let's think about the year 13. Let's think about the NCl3. Nitrogen is a group 15 element, so this has 5 valence electrons. Chlorine has 7 because it's a group 17 element, and they all need 8. And if you add that up, that's 26, and this is 32. So what does that mean? 32 minus 26, you have 6 bonding electrons. So these are 6 electrons that are being bonded. So you have 3 bonds. So if we come back to here, there'll be N, and just put the CLs right next to it at the beginning. 3 bonds, that means 1, 2, 3, and now you need to look at every single element just to make sure they have 8 electrons. Okay, so right now the Cl has only 2, so we need 1, 2, 3, 4, 5, 6. Ignore those lines, I just mean to highlight those for you. So this is what you need to do for Lewis diagrams. If you don't draw these dots, they are incorrect. Okay, so this chlorine needs to have 8 electrons, so does that. That's why you need to give it 6 dots. So right now if you look at that, that's 8 electrons, 8 electrons, 8 electrons. And if you look at the nitrogen, that's 1 line, 2 line, 3 lines. You need 8 electrons, so that's NCl3. Okay, but again, this is where if you are really good at organic chemistry, you can just look at these rules here. Nitrogen need to have 3 bonds, so that's why they bond 3 times, and then chlorine only bond once, that's why they single bond. Just, you know, you can come with the base structure quite easily, and you can just assign the lone pairs of electrons. Okay, OF2, same thing. If we do OF2, so this is OF2, so this is 6, 7, 7, 8, 8, 8. So that's 24, 20. Take a difference. That's 4 electrons. So it's 2 bonds. So again, this come back to here. Oxygen only bond twice. So put the and people always go, how do you know O goes in the middle? Well, there's only one oxygen. Oxygen needs to bond twice. So you need to bond once to each of the fluorine, and then each of the fluorine need to have 8 electrons. So we give it 6 dots. Right now the oxygen has 4 electrons, so we need to give it 4 more dots. Some people go 2 dots up top, 2 dots underneath. That's absolutely fine. The only reason I draw this, I actually prefer to draw it like this, because I hate to draw. I tend to draw the shape of the diagram, shape of the molecule as well. So this is a bent shape, not a linear shape. So this is bent. This is trigonal pyramid, and the CH4 is tetrahedral. Okay, so as you can see, the question asks you how do they have different shapes, but then they have a bonding of 109.5 degrees. So you need to understand what shapes a molecule actually means. So when we're talking about these electron densities, so if you look at carbon, for example, if you look at CH4, so you got the carbon bonding with the 4 hydrogens. Now this particular diagram is incredibly deceiving. It looks like 90 degrees, but it's not 90 degrees, because you need to understand all of these things are what we call regions of electron density. So they have a negative charge, well, the electrons do, and they want to position themselves as far away as possible to minimize this repulsion. So they want to get away from each other as much as they want, because they just really don't like each other. So the furthest they can do is actually 109.5 degrees, because you need to remember this is 3-dimensional, so they can take space up top, to the side, like coming out of the computer screen towards you, and then going into the computer screen behind it, so you can't see it, and they can take a bond angle of 109.5 degrees. So all of these 3 structures have 4 regions of electron density around the central atom. So carbon is pretty straightforward. If you look at the nitrogen in the lowest diagram, you have got 1, 2, 3, 4 regions of electron density. These guys all position themselves as far away as possible to minimize repulsion. Therefore, they will take what we call the tetrahedral arrangement. But because electrons are so small, so you can't actually see this top half. You don't see that in your shape. That's why it's called a trigonal pyramid shape. Okay, so OF2, same thing. This has 4 regions of electron density. So that's 2, really obvious. And then you got this one lone pair and the other lone pair. So that's 4 regions of electron density. 2 of these are connected, and the other 2 are lone pairs of electrons, which are not involved in bonding. So they don't do anything, and you can't see them because they are too small. So it's kind of like, if you imagine the tetrahedral, you can imagine the tetrahedral, like, say, if you're supposed to draw them, one going up, one going to, it's like one, if you think about where you're sitting, one H is coming out of your head going straight up, and then H is going towards your right hand side, and then you have one that's going into the page and one that's coming out of the page. So one's coming out of the computer screen towards you, one is going into the computer screen towards the back of your computer, and that's how you see them. Now imagine when you have OF2, it just means when you have OF2, if we do it like this, it just means you have these electrons here that's coming out of the page into the page, but you can't see them. If you can't see them, what do you see? You see a bent shape. So this is a bent shape of 109.5 degrees. So this is a tetrahedral shape with 109.5 degrees, because the reason why they have the same bond angle is because they all have 4 regions of electron densities around the central atom, which push each other away. Okay, so sorry about all the messy writing, but you get the idea. Okay, so if we come to the answers, here it is. Bond angle is determined by the number of regions of electron density and around the central atom, because they want to minimize repulsion by being as far away as possible as they could. So you can see all three molecules have 4 regions of electron density around the central atom, and they will position themselves as far away as possible to minimize repulsion. So they all have a tetrahedral arrangement. Okay, so the arrangement is kind of, you can think of it as the parent shape or the fundamental structure, but and then you need to actually remember. So remember, the shape is what we can see, not with our naked eyes obviously, but it's what we can observe. So if you have CH4, all the electron pairs are bonded, you can see all of them, so the shape is tetrahedral. But because in NCl3 3 of these electron densities are bonded, you can only see those 3. See this one that's non-bonding, we can't see it. If you can't see it, it can't be observed, then it doesn't contribute to the final shape. But it does contribute to the arrangement, because those suckers are sitting there and pushing all the other electron densities away. Okay, so for OF2, same concept: 2 bonded, 2 bonding, 2 non-bonded, and then you have a bent shape with 109.5 degrees bond angle. We do also accept 109 degrees for this particular exam, because like I say, you only level 2, first time you ever did this. But the more chemistry you do, then you actually find out the bond angle is not actually set at 109.5. They do change gradually depending on what atoms are bonded, how they are bonded, but that's further down the line for chemistry. Okay, so that's that question. It is an excellent question. Let's move on to the next one. So this is looking at the section on polarity. So that was shapes of molecules. This is polarity. So you need to decide. The following molecule table shows a Lewis diagram, so they have to give you these, because if you can't draw a Lewis diagram, you can't get shapes. If you can't get shapes, you can't get polarity, which is a bit unfair if you can't draw a Lewis diagram. So they gave it to you. So, and this is actually when they get smarter, because in the past they've often done one polar and one non-polar. So people just guessed like one polar, one non-polar. But in this case, this is a polar molecule, and this is also a polar molecule. So they kind of, the examiner, whoever wrote this particular exam, actually, outsmarted quite a few people last year. Okay, so how does this work? So let's explain these two structures separately. So I'll do NH3 first, because NH3 is a little bit easier. So again, similar as the previous question, I always do the full set of answers underneath in sort of my language, so it should be more than what you can find on the evidence page on the NCEA, on the NCEA websites. So feel free to use, pause the screen and just write it down if you want to. Like, let's look at NH3. So when you're talking about polarity is dependent on 2 things, and this is where a lot of people miss on the excellence. They all know one thing. They all talk about the shape of the symmetry, the shape symmetry. And they always go, well, this shape is symmetrical, this shape is not symmetrical, therefore they cancel each other out or don't cancel each other out, therefore it's polar, non-polar. You won't get excellence with that. You only get a merit, because a lot of people just go, the bond dipoles will cancel each other out, or they won't. I mean, where did this bond dipoles come from? You just talked about the concept and without even talking about what it is. So the first thing I always encourage people to talk about is talk about bond dipole formation. So what is bond dipole formation? And again, if I have more time, because we're just around the corner for exams, if I have more time, I'll be more thorough with this particular explanation. But you found to be really pragmatic. If with any molecules that we give you for the exams, you can see the bond, like just look at that particular bond, you can see the nitrogen and hydrogen are different atoms, you can see the carbon and hydrogen are different atoms, you can see the C and Cl are different atoms. You can kind of just assume that if you have this different atoms in level 2 chemistry for this particular standard, that means what happens between the nitrogen and hydrogen when they share electrons, they won't share them equally. You will have a polar bond. Why do you have a polar bond? Because in this case it's nitrogen, but you don't need to know this. The nitrogen actually wants the bonding electrons more. It has a stronger force of attraction on these bonding electrons compared to the hydrogen. That's why it's slightly negative, because they're kind of sharing the electrons, but then these electrons are closer to the nitrogen than they are to the hydrogen. So that's why it's slightly negative, because it kind of kind of stole one of the hydrogen's electrons, but it didn't actually steal it. It's just still sharing it. You know, it's kind of like you and your sibling sharing whatever, like say sharing a laptop, and you are the older sibling, you're using it 6 times a week, like 6 days a week, and your younger brother sister gets it once a week. You know, so it's still sharing, but it's not fair. It's uneven. Okay, so you form polar bond because of the significant electronegativity difference. Is how between the two atoms in the bond, and because of that, because you know, you can find the full answer underneath, but because of the significant electronegativity difference, uneven sharing of electrons, you have polar bonds, then you create what we call bond dipoles. And people always ask me, what the heck is a dipole? I often just simplify. Think about the pole. You have the north pole, you have the south pole. Okay, so they are oppositely charged. So this is one pole, this is another pole, and in English, 2 poles, you either go bi or di. So in this case, dipoles means 2 poles. That means 2 oppositely charged in this particular bonding. So it's a polar covalent bond because you have uneven sharing electrons, you create bond dipoles. Now, if the bond dipoles are evenly distributed in the shape, if the symmetry of the shape allows them to cancel each other out, then it will be nonpolar. But in this case, we have bond dipoles. We have unsymmetrical or asymmetrical shape, because if you look at oops, that's ugly. See, if you look at the shape of molecule for NH3, which is trigonal pyramid, this is asymmetrical shape. Therefore, the bond dipoles do not cancel each other out. Okay, don't cancel. Okay, no cancellation. Cancellation means no. So that means this is still polar. No bond cancellation, still polar. So what does that mean? That means part of the molecule is slightly positively charged and the other half is slightly negatively charged. Okay, so this is another way to, again, very pragmatic. If you think about all the shapes in level 2 chemistry, the only ones that have got these, the lone pair of electrons, are your bent shapes and your trigonal pyramid shapes. So if you ever get these shapes, unless they're the same atoms, but then no one gives you those for level 2, that won't be an excellent question. If you have bent shapes and trigonal pyramid, you can safely just say it's polar. Why is that? Because as soon as you got these lone pairs of electrons, what these guys actually do, these electrons belong to the nitrogen, so they're actually closer to the nitrogen than what the bonding electrons of the nitrogen hydrogen would be, because these guys belong to the nitrogen. It's kind of like, think about where you're sitting. Yeah, think about if nitrogen is you're the you know, this is your head, and then the lone pair electrons are your hair. So the hair belongs to you, your hair belongs to you, obviously, and then this is your arm, you're holding on to your sibling, then you're sharing something. Which one is closer to you? It will be your hair, wouldn't it? Because they belong to you. You're not sharing them with anyone. So the lone pair of electrons actually exert more repulsion on these other electron densities and push them further out. Okay, making the shape asymmetrical, and the dipoles do not cancel each other out. Hence, it's still polar. Now, so you can just assume for bent shape is polar. For trigonal pyramid shapes, it's polar. But then you can't just you know, that'll help you to quickly identify what it is, but it doesn't mean all the other shapes are non-polar. You can have linear shapes which are polar. Which is a bit unusual. You can have trigonal planar shapes which are polar, and you can have tetrahedral shapes which are polar. And this is a really good example of how you can have, because most people just go, oh, tetrahedral, that's amazing, that's that is a symmetrical shape, so they should cancel each other out. But you need to remember one thing, guys, especially now. I'm gonna tweak this question a little bit to confuse you even more. Like, say if I give you these, like, say they're being a bit nice here, but if I change the Cl to an H and I do it like this, I guarantee a lot of people will just go, ah, that and that cancel each other out, that's gone. That and that cancel each other out, that's gone. This thing is non-polar. But then you will be mistaken, because you need to remember you are looking at a 2-dimensional diagram. You are not looking at a the structure of this particular molecule. So it's not 90 degrees. So you got two types of bond here. So you got CH bond, you got CCl bond. You form different strength, you form different dipoles essentially. So in this case, because I know the electronegativity value, I mean that's something you can learn from the periodic table trend, this is actually slightly negative, this is actually slightly positive. If I put the C and Cl, this is actually slightly negative, this is actually slightly positive. You can see how the carbon is behaving differently when it's being bonded to different things. It's again using siblings as an example. Like say if you're the middle sibling, if you this is the hydrogen is your younger sibling, you kind of like give me whatever you I want to share this, give me, and then you benefit from this because you are more electronegative. And then if you got paired with the older sibling who's much older than you, much more confident than you are, and they're like, hey, give me, and then you have to share whatever you own with them, and that's so you are still the same carbon, but then when you're being bonded with different things, you are behaving differently. So the dipoles, but then again, a lot of people ask me, do I need to memorize the electronegativity values? No, you don't. You just need to you can see them. The carbon is bonding to different atoms. If you're bonding to different atoms, you have different dipoles. If you have different dipoles, that means if we look here, if you have different dipoles, then the different polarity in size, they do not cancel each other out, therefore it is polar. Okay, now this whole thing is an excellence question, so you need to make sure you talk about the formation of bond dipoles. Okay, so this is where a lot of people don't talk about. They just go straight into cancellation. But what are we cancelling in the first place? Okay, so read this, pretty much everything I've explained for in the past couple of minutes. Just make sure you can do these. All right, moving on. But polarity, just before we go, very, very standard question. No surprises here. Very popular exam question, so make sure you can do those. Okay, next one. This is the last one for this particular section. This, I believe, is also an excellence question. Yes, it is. So this is looking at enthalpy calculation. So you need to remember bond enthalpy is the sum of bond breaking minus bond making. So when you see, and this is what I tell my guys, when you see this table, when they give you like this table here, when they give you the bond and then the enthalpy, straight away, this is the question you need to do. So what you want to do, you want to look at the structure of the everything that of the structures of the reactants and products, and then figure out what bonds have you actually broken and what have you made. Okay, so look at these, they're actually being really nice. This is C3H8. Excuse me, let's get rid of that. That's a bit ugly. Oops. Okay, so this is C3. Oh my god, don't you hate it when that happens? So this is C3H8. There we go, third time is the charm. That's C3H8, this O2 is down here, and the water is over here. Okay, so let's think about this. So what are we breaking? So you are breaking the bonds of C3H8 and 5 moles of O2. So if you look at the C3H8 structure, if you have this as many color pencils or coloring pens, if you possess them, it's maybe advantageous just to highlight them in so you don't miss any bonds. But for me, this is pretty straightforward. But then you see that CH bond, need to break that, 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 that. That's 1, 2, 3, 4, 5, 6, 7, 8. I need to break 8 CH bonds. Okay, now if you did this with colored pencils, you can just highlight that, highlight that, highlight that, highlight all of these lines, and then you can realize, hold on a sec, these different colors here, these carbons in the middle, those bonds are actually not broken. So I need to break 2 CC bonds. So the CC on the left, and then the CC on the left, and then the CC on the right. So I need to break those. Okay, so that's my C3H8 done. I need to look at my oxygen. To break oxygen, I need to break this. So I need to break O2. Oops, I need to break O bond. How many moles do I have? I have 5 moles. So for each O2, you have one O2 O double bond. I need to break 5 moles of those. So we've got to do that. Okay. So if we do these together, so that's CH is over here, 413, 8 times 413. CC is 2 times 348, and 500 is 495 times 5. The total, add them up, is going to be a whopping 6475 kilojoules of energy. Now let's think about making. What are we making on the other side? So we're looking at the H2O and CO2 now. So for H2O molecules, for each mole of H2O molecule, you have 1 OH bond and 2 OH bonds. So think about OH bonds. I don't want to draw them right next to each other. Actually, let's just do OH bond. How many am I breaking? I'm breaking 2 per water molecule. I have 4 moles of water molecule over here. So it's going to be 2 times 4, which is 8 OH bonds. And how many CO2s am I breaking? So C double bond O, look how nice they are. They draw it for you. C double bond O. For 1 mole of CO2, I'm breaking 2 CO double bonds. I have 3 moles altogether. Therefore, I need to I need to make 3 times 2, which is 6 moles of C double bond O. Okay, so let's have a look. OH bond, I know this is going to be 8 times 4. 8 times 4, where the heck is it? It's right there, 463. So blind for a sec. And then C double bond O. This is actually what we're trying to figure out. I want to calculate the enthalpy for the C double O bond. So I can make this X. So this is 6 times whatever, 6X. Okay, so that means, so the change of enthalpy is the total of bonds breaking minus bond making, which gives you the change of enthalpy. The change of enthalpy is already given. So here we go. Let's do this. So let's substitute numbers in. Change of enthalpy is given, so it's negative 2056 equals the total of bonds breaking, which is 6475, minus 8 times 463, which is going to give us 3704. So 3704 plus 6x. Now make sure it's bracketed, because these two are in brackets, because it is the total of these two. So just solve. So it's 6x. For those of you that are not so confident with maths, is 6x equals moving. So it's can I trust you guys with maths? Probably not. Most of the time in chem I'm doing maths teacher's job, so let's just rearrange it before I jump that step. So let's just rearrange it. Negative 2056 equals 6475 minus 3704 minus 6x. So that means 6x. So that means I move this to the other side, move to the side. So, or you can divide it by negative 1 on the other side. Make 6x a subject. So it'll be positive 2056 plus 6475 minus 3704. So 6x equals, if you put those together, 6x equals 4827, and then x equals 4827. Then I wrote 25. Don't be like me in the exams, because I actually have seen this happen. So x equals 805. Make sure you put the unit, kilojoules per mole. Okay, because everything here is measured in kilojoules per mole. Okay, so this is an excellent question. So hopefully that was helpful enough. And we will be jumping into the section 3 of this particular exam. So hopefully this is helpful. Again, if you could subscribe, leave a like, share this with your friends and other students in your chem classes or people in your school. It will be greatly appreciated. Otherwise, stay tuned for part 3, the last question of the exam.